Okay, so it's time to go ahead and begin. So the main topic today is finite state machine. So FSM, the lab six, and also the final project involved finite state machine. Okay, so in the back, you do have to be quiet, please, while lecture is going on. So just as a reminder, tomorrow, that's when lab four is due. And a week from tomorrow, that's when lab five is due. And you have enough information to do those things. Okay. Lab six going to be due the Friday before Thanksgiving break, which is the 17th. And you won't have enough information if you guys until the end of Tuesday lecture next week. Okay, so theoretically, after Tuesday lecture next week, you could finish all the labs. Okay, and then you would still have the final project out for Thanksgiving. And we're going to talk about the final project. Anyway, that's the lab situation. Today, class, like I said, the main topic is FSM, the finite state machine, and that's what the activity is on. But before we get to an FSM, there's a couple of other things I want to go over. One is called a clock module, and the other So first of all, everyone should have a shared table. I have this handout that has the Verilog or Verilog code for a clock divider. So you want to be looking at this while I talk about it. So a clock divider module, this is the high level black box diagram. It just has one input, one output. Okay, the input is just clock, CLK, and then the output is SCLK, where this stands for slow clock. Okay, because the purpose of the clock divider is that it takes the frequency coming in and it makes a frequency that's lower than what's coming in at the output. Okay, so we'll make a frequency lower, say it's getting divided. So what's the significance of this frequency 100 megahertz? Because last class, after the midterm, I mentioned the significance of this. What's the significance of 100 megahertz in this class? Yeah, exactly. Your basis 3/4, it operates at this frequency. And then what is the period of the frequency of 100 megahertz? And right, that's the time it takes for one pulse. Okay. So now, if you look at this handout that has the system Verilog code for this clock divider, the first thing you'll see after the module name is something new, and that's this number sign, and then in parentheses parameter max counting. Well, this is a way in system Verilog that you can declare a variable instead of an initial value. So we're just creating this variable parameter called max count, and then we're just setting it to 1. Okay. All right, now if you look just below, where the inputs and outputs are defined, where it has logic and then in square brackets 29 to 0, and then count is initialized to 0 with that equals 0. So how many bits is count defined as? How many? 30, like 29 to 0, so a total of 30. And if we treat count as an unsigned binary number, okay, you're going to see we're just using count as an integer. We don't want it to be negative. So if we treat count, which is 30 bits, as an unsigned binary number, then what's the range values of Or how would you figure it out? 2 to the left. That would be the high side, right? We all start at 0. So it'd be 0, and then 2,000. You need some else. But what if we have 4 bits? What would the range be for 4 bits? Yeah, there we go. Yeah, if you have 4 bits, right? It'd be 0 to 15. So 2 to the 4 would be 16. So you got to subtract them. So yeah, same thing. No matter how many bits, you always got to subtract 1. 0 is part of the range. So. Now, if you go ahead and figure out what 2 to the 30 is, it's a big number. Something like 1,073,741,000. Right, so we could represent values, but we could represent values equal to 1,073,000 or 1,073,741,820. Just subtract 1 from that. Okay, so the significance is you're just going to make sure that whatever largest value you want to count to be, that you have enough bits to cover that value. So that's why it would take time to figure it out. Okay. Okay, I already told you this, that count is initialized to 0. That's where you see the equal to 0 after the 29 to 0 bit numbers. All right, so now we're gonna see how this code, okay, what you see within the always FF block. It's you know, just have the clock input, so you know, we have a sequential circuit here. And what does in the always FF block? What does the pause edge clock within the parentheses? What does that? What's the significance of that? Right. By putting pause edge clock within the parentheses, we're making this a rising edge trigger, like a sequential circuit. Okay, because remember, whatever goes within the parentheses, and that always FF, that's when the always FF block, what's inside the always FF would be evaluated. Okay, it's evaluated on every 0 to 1 transition to block. Okay, so you know, here I've written clock signal what's going into this module. We're going to figure out what's coming out of it, see what's called the clock divider. So I put these little blue arrows on every 0 to 1 transition. And, you know, this just means it goes on chart. Okay. Okay, so remember, we initialize count to 0. So when a positive edge of the clock happens, the always FF block is going to be evaluated. The first thing that occurs is that count is incremented by 1. Okay, and then we test the condition. Well, is count maximum? And let's say for this example here, we set max count to 50 million. Now, when you set a parameter like this, there's 2 ways that you can change this max count value. Yes, and one way you could do is simply change it right here. Instead of setting it to 1, we could just set it to 50 million. Okay. But the other thing you can do when you define a parameter is that you could set this to some default like 1, but then if you wanted to change it to some other number, you could do it in the top module, your structural module, where all the modules connect together. If you wanted to do it there, you would just after your filing or in your filing table, you would just put number summation and then the new value that you want. Okay, and that will essentially change that value in that model. And you see the reason why you might do that, the reason why you might want to just set this to some default number and then make the change in that is because let's say you have a case where your design has like 5 of these, like you have 5 clock dividers. And each clock divider is defining value different, maybe 1, 2, you 50 million to be the max count, but then in another one, you want it to be 30 million, you want it to be some other number. Well, instead of having 5 different clock divider modules where the number is different here, you just have one clock divider module that's set the default, and then you change the number, max count of modules in the top. Okay, that's less files. Okay. All right, but let's see how this code makes it so our slow clock output is a less frequency than the clock frequency that's going into it. So again, going back to our code here, when the positive clock happens, count is going to be incremented by 1. So since we started with count 0, the first clock edge, now count is going to be 1. And then it tests, well, is equal to maximum. But clearly 1 is not equal to 0. So, the if statement's not evaluated, then the next positive edge of the clock comes along, and the same thing happens. We increase the count by 1, it tests it against our max count. So if you see, and one thing that we have to mention is that slow clock, if you look up to where slow clock is defined as an output, it's initialized to 0. So you see slow clock is initialized to 0. And now it's going to stay 0 for 50 million clock edges. So for 50 million of these clock edges, it's just going to stay 0. Right? Because it's going to take 50 million clock edges for count to equal max count. Right? So we got 50 million. And then the period for each clock cycle is 10 nanoseconds. So the amount of time that it's going to stay low is the 50 million times 10 nanoseconds, right? Because each edge of the clock is separated by 10 nanoseconds. Okay, so it's going to be 50 million times 10. And what's 10 to the what? -9. So 50 million times 10 nanoseconds. It's that coming. 10 to the 6 times 10 to the -9. You don't have to do multiplication of powers, the same base. So what's it going to be? It's 50 times 10. No, 50 times 10. Say it again. What? Yeah, exactly. 500 times 10 to the -3, right? And you just subtract the power, right? So that's in seconds. So this would be 500 milliseconds, right? 500 times. Right, 10 to the -3 is going. And how many seconds is 500 milliseconds? How much? Yep, half a second. So you see, slow clock is going to stay low for half a second. And that's when finally count will equal max count. And when count equals max count, now within the if, count is initialized back to 0. And then look what happens to slow clock. Slow clock is assigned to the version of slow clock. So after this half second, slow clock's going to go to a 1. And it's going to stay a 1 until, right? So now it's going to stay a 1 for half a second. Right? And then just going to repeat, because after that half second, the count equals max count, and you put slow clock again. So we end up getting the square wave coming out of this. And it's low for half a second, then it's high for half a second, then it's low for half a second. So what's the period? What's the period of something that's low for half a second, then high for half a second, then low for half a second? What's the period of that? 1 second, right? Because the period is just how long it takes the wave to repeat. Now, I didn't do this by scale, obviously. So 1 second. And then what's the frequency of something that's 1 second? 1 hertz. So you see, if in this code here, right? It's system parallel code. If we make max count equal to 50 million, 1 megahertz is going to come in, 1 hertz is going to go off. And that's what's meant by clock divide. It's when you take a signal and you lower the frequency by some amount. And just by taking the count, you can have this divide from whatever you want. Right? You can change this number instead of 1 hertz coming out, 10 hertz or 1 megahertz, whatever it may be. It's just figuring out the max count. The way you figure it out is just what I showed you. Right? The number of clock pulses times the number of clock cycles times the period. See, there's a couple of reasons why it's mentioned. One reason is in lab 6, you will have a talk about it. Now, in lab 6, we actually have a talk about it. It's a module that Dr. Neely wrote. But a lot of times, this depends on which or what team project you pick. But a lot of times in team projects, especially if you're doing something that has to do with like clock, and people often do. Well, in designs like that, you often need development. Okay, so it's hopefully, again, not 100%, but you may need this for your team project. So I would be hanging it might need. Okay. All right, so any questions to this point? Okay. Oh, first it's like first like talk about like 5 like the something like specific or like a clause. No, clock position like there's many practical designs where you'll take a square wave at some frequency and want it at a lower frequency. I mean, an example is like a digital clock where maybe the high frequency represents minutes, and you want a frequency that represents so maybe your high frequency represents seconds, and you want another frequency to represent minutes. So you would essentially divide it by 60. And then if you want hours, you divide it by 60 again. Okay, so that's where like the clock dividers, if there's something to do like this time, like another example could be a stopwatch. So yeah, this clock dividers are very popular. Any other questions? Okay, the next thing I wanted to talk about is the counter. And the main things, the main points I want to make. One of those main things right here. A counter is just a register, a memory register that we talked about last class. Right? In the midterm, remember, I talked about memory register, the and other things as well. Well, a counter is just a memory register with some additional circuitry that influence the output in some way. And as an example of a counter, I use this diagram. This is a diagram of the microprocessor that you build in CPU 233. And there's one of these at each table, and have enough for every, but there's one at each table. So if you look at this, you'll see that in the bottom left-hand corner of the diagram, there's this module labeled PC. PC stands for program. Okay. And I just rewrote on the board here. I just rewrote the inputs and the output. Also, there's +4 that I'll explain of that. So when you look at this, you may think that this is something totally different than we've already used. We didn't talk about PCI or PCN, PCB, or PCWR. But in fact, these are just different names for other names that you've seen. PCL, that's the same as people register. PCN, that's the same as the D input of the register. PCL, what do you think RST stands for? Yeah, that's just reset as we talked. It is activated. Because here it resets. After pi, we make it a 1, what's going to happen? What does reset mean? Yeah, Q just goes to 0. And then WR, WR stands for right. And this is right is the same as enable, enter, look. And you can think of this right just being an enter. All right, so you see this, it's just a memory register. But in addition, it increments the output. And this particular counter increments the output by 4. That's what the +4 is. Okay, now when you take CPU 233, you're going to learn why this is +4. Okay. But as far as modeling this in system development, when you model this, is you have the same code for the register, so you have the register code. So the same code you have in the memory register, that's part of that 5. That's how you would model this. The same code. Now, you got different names where it's an output, but other than that, everything's the same. With the addition of code that takes care of this +4. And what you would do is you would just add an assign statement that assign. Now, I call this internal signal over here T2. I call this T2. When you take this class, you were descriptive, like we talked about, because when you put this all together, you're going to have like 50 internal signals, and you don't want to use just T1 or T50, otherwise you'll go crazy. When you're trying to troubleshoot it, you're looking at a timing diagram with 50 wave signals, it's T1, T2. It'd be like 15. But use descriptive internal signal engine, make it easier. But it's just T2 and T1 that, this is just conceptual reasons. But the way that we would hear this before is you just assume T2 and this internal signal on this side. The internal signal on the side. Okay, plus, and then you need plus is system level is add. Yeah, that's why we don't use the plus as an whole symbol in the like the boolean. And you see, when you take that class, we're not expecting you to come up with like an RCA circuit that will do this addition of 4. By designing the addition of 4, you're letting the software do the work. So the software will come up with a counter that has that assigned to one. It's a guy. Wait. Well, it's because of the purpose of this. The purpose of this is that if this output is used to do something later on, and you're going to learn what you take the class, we want to increment the input. So typically, you reset this at t equal to 0, so your output will start at 0, and then this is going to that output is going to be used by module. In fact, look here, choose by its memory module. And then the next clock pulse, we want to increment that counter output by 4 because the way we use it, needs to be increments of 4. And again, when you take the class, you'll learn why it's where it says number. Yeah, we do. We want this input to be incrementing by 4 every time we get a clock pulse. So it's like it's set to 0, it's used to do something, then it's a clock pulse, and increment by 4, it's loaded, it's or something, it just keeps going. So you do this output of 0, 4, 8, 12, 16, so. Okay. Yeah, the main thing that the main thing I want you to take from this is, first of all, a counter is just a register where, in addition, the output increments by some amount. Here it's by 4, but it can be these amounts. Also, you'll have a counter that count the sequence. And I'm going to get to an example like that, where we're using an FSM, a finite state machine, to do a certain sequence. Okay. And then the only other thing you might have mentioned, because this will look up and you can see into the, you just know a counter, it's a memory register, it's the same code. Okay, just with some additional code to get whatever increment it is. Okay. Alrighty, so let's see. Ready for an episode now? All right. So my next state machine, looking at the camera. This is what we've been working towards all quarter. You can do all kinds of things with a finite state machine. See here. So more review. So let's see. Yeah, remind me when I get to the end of this, I'll go through. All right. So here's a generic, high level diagram of an FSM. So notice it's got three modules to it. So mixed state decoder, so a sleep register, and a bucket decoder. Now, based on previous discussion, you should be able to tell me which one of these modules are sequential and which ones are combination. How do you tell? How do you tell from the diagram whether it's sequential or combination? Yeah, yeah, it's got a clock in, but that means it has memory and sequential circuits have memory. So it should be a way to register. So this is sequential. These decoders are combination. Okay, so when we take CP233 and the professor asks you, they're likely to ask you, looking at which blocks are sequential and which ones are combination. All you gotta do is have a block now. Remember, it's got the little triangle, like see the memory block at the very bottom of the it doesn't say CLK, but if you see the little triangle, that means a clock. It's sequential, your base file is sequential, immediate generates combination there. So you get what you have a clock. So if you look at the diagram, then you look at the upper right hand corner. The CU, ECDR, what was that we talked about that a couple weeks ago? What is that? CU, ECDR, what does ECDR stand for? Decoder. And right about it, look what they have. CU, FSM. So CU stands for control unit. And the control unit has two parts. ECDR, which is a combination of decoder, and FSM, which is sequential finite state machine. And we talked about the total last time. They have these outputs of the ALU1, the ALU source A, the ALU source B, and so on. Like, where are the outputs of the decoder connecting to? And we're going to look at the diagram now and see where are those outputs of the decoder going. Anyone looking? Like, where's ALU source B? You can see it elsewhere on the diagram. Some people looking at their phones. Are you looking at the diagram on your phone? The mux. Exactly. Specifically, what input of the mux? Select. So the outputs of that computer, they're going to all the different select lines of the mux. And what does the select line of the mux do? What does it determine? It determines which input's going to be connected to the output. So as I said back when we were talking about this, Why it's called control the color, controlling the color. So James output color are connected to the MUX selecting inputs. It's controlling how the data flows through that circuit. And the input color are instruction bits. Okay. It's 30, it's 14, 12, it's 16, 0. Those are all bits that are under the instruction. And depending on what the instruction is, data has to flow a certain way in order for that instruction to happen. Okay, so the coder is controlling how the data flows. Now, look at the after number right above it. It also has instruction with input. Instruction with 16 0 and also instruction with 15 12. And then go to that output or outputs of the FSM. And the outputs that we have there. We got PC relates going to the number. We got red writes. Red write goes to the red file. We got memory, WD stands for write enable. Okay, so that's another thing that goes on output. And then we got memory or MEM, which stands for memory, RD, which stands for read. Okay, and what you're going to learn in that class is that a write is just like a store. Okay, when you're putting information somewhere, like in a register, and RD, which is your read, is when you're getting data from. And reads and writes, they're what we call time critical. But those reads and writes happen at a certain time. Okay. The output of the decoder that goes to the muxes that route the data. As long as the data gets routed within a certain amount of time, it's simply 1.5 points, everything's going to be fine. So the routing of the data is not time critical. Again, as long as it happens in a certain amount of time. But the reads and writes, they have to happen at certain time. And the reason I point that out is because anytime you have something that's time critical, you want an FSM. Okay. I mean, they're used for all kinds of things, but particularly when you have something time critical, an FSM is necessary to have. Okay, so back to this. So we have this next little decoder, output information. We have the state register, but that's sequential. State registers any register memory device. Right, that's storing input. And here is storing where we're at, like where we're at the sequence. In present. In the sequence. The next decoder, name implies, that's going to determine where we're going, right? The next state is. So determining next state. Where and we had covered here. And your name implies it just determines your output. And there's two types of finite state machine. And the two types are differentiated by how their outputs are determined. Okay. So one type of FSM is called a Moore. It's somebody's last name. And then the other one is also a person's last name. And it's no relation to Dr. Moore. Okay, but there's an FSM also called a Mu. Okay, so there's a Moore and a Mu. The Moore is said, these two are distinguished by how the output is determined. The more the output is determined by the state learning form. And immediately the output is determined by the rate you bring in external inquiry that's any singular or plural. Okay, so the more is an FSM, the output is only determined by the state unit. Immediately the output is determined by not only the state unit, but also either an external input or external inputs that can be singular. So notice in the diagram, I have everything in black, I have these two lines in red. Okay, so the reason I did the color coding is because if it's a norm, you just have everything that's in black, you don't have a red. Okay, so if it's a board, you black only. If it's a mealy, you have everything in black and you have the red. Okay, so mealy, it's the black. Okay, because if you don't have the red, the only thing that's going into the other are the outputs of the shift register or the state registers. Okay, and the state registers, that's only the information of where you're at. And see, that's the state you're in, where you're at. Really, not only how the output of the state register is going to be able to decoder, it will also have external input to one here I showed two to be 2, 1, 15. Okay, but the key thing is that before you don't have what's in red, when it's a movie, you do have what's in red. Benson, she had a way of remembering the dates. Okay, the way she remembers is that she always remembers as less. Doesn't have the external inputs. Yeah, so the number has less. I think that's a pretty clever way to remember the differences. Okay. Okay, so any questions at this point? We're doing good on time. This morning I was already at the top of the more time. So for the bike, I take a break at some point. It's probably going to take me till probably until 1:30. See how it goes. All right. The next thing we're going to do is I'm going to show you an example of a counter that's made with an FSM, made with the same machine. And this FSM counter, it counts in this sequence that you see. If this counter is going to count 2, 0, 7, 5, 3, and then this be repeated. It's the same sequence over and over. Now, anytime you do an FSM design, you always want to start with what's called a state diagram. Okay, I'm going to show you what the state diagram is. But that's always the first step. You should never try, modeling and system verify in FSM until you have the state diagram. Because what you're going to see is that once you have the state diagram, to go from the state diagram to the system verify, you need to build that FSM. It's pretty cool. Right? You see, let's start with the state diagram. State diagrams always. And one of the symbols used in the state diagram is a circle. The circle represents a state. The circle represents state. Okay, also you'll show an arrow like this. The arrow represents a clock transition. So represents When that clock transition, it can either be rising edge or falling edge, depending on what type of FSM you have. You know, just like you have rising edge and falling edge registers, you have rising edge and falling edge FSM. I mean, it determines whether it's rising edge or falling edge is, you know, with the state registers. Right? Okay, then within the circle, okay, it's usually split up like this. The top half, you put a label. And label can be anything you want. In the bottom half, there's more outputs. Okay, when we have that arrow, it's still right by place. Shift external input. Singular. Then we put a line below the line, we'll show new. Okay. If you think about it, it makes sense that we put outputs within the circle because the circle represents a state, and the more output really depends on state here. It kind of makes sense that we put new outputs outside the circle because the new output only depends on the state. It also depends on external input. Since the external. Yes. So it kind of makes sense that you put the new output outside because it not only depends on the state, but it also depends on external inputs. Okay, so this is what is typically used as a legend. Now, there is some flexibility within state diagram because of the state diagram, and just to give you sort of a roadmap before you start into the code that's going to model the FSM. So some of this, there's need some flexibility, but where the flexibility is, outputs go within the circle, really outputs go outside of this. Okay. All right, so now I'm going to show you the state diagram for this time sequence. And I'm going to start like very basic, like the most basic state diagram that would do this sequence. And then I'm going to add stuff and make it, more complicated, or, more practical. Okay, but the first thing is we're going to have a circle in each state. And we're going to consider each any count in the sequence as being a state. So since I have 5 numbers in my sequence, I'm going to have 5 states. It doesn't matter the orientation, the state element, you can get the orientation. I'm going to do this. You make it box shape, rectangle shape, irregular. So we got our 5 circles for our 5 states. I'm going to label these states just with some call this state A, so STA for state A. I'm going to call this state B, state C, state B, and state B. I'm going to make these outputs of the counter. I'm going to make them more outputs. But since they're more outputs, they're really going to depend on the state and therefore mean that the more output in inside the circle. And I'm going to put these as binary numbers. Right, so 2 is 0 binary. Now, I could have chosen this thing. I mean, if you wanted to put it in space, then you could. Okay, I just decided to be binary. And then B3 that all zeros, the top line, state C, we got 7, so 1, state B at 5, and state D at 3. Okay. And then to start with, we're going to transition between each of these states, what's called an unconditional or unconditional transition. So the way I would show that is just by putting the arrow. Remember, the arrow represents a clock transition, so it represents a rising edge. Let's say our FSM is rising. So these arrows represent 0 to 1 clock transitions. So if I don't put anything next to these arrows, that means that if I'm in state A, the next time a clock transition happens, right, at the time of the 0 1 clock transition, again, assuming this is driving edge, well, it's that transition, it's going to go from state A to state B. And then the next driving edge will go from B to C. The next driving edge will move C to D and so on. Okay. This is called unconditional. Okay, unconditional transition in the states. So this is probably the simplest state diagram, right? When you have unconditional transition between the states. Any questions up to this point? I'm going to start adding some stuff now. Ready? So I'm good. Okay, well now let's say, oh, and also this is general type work on this. Since I'm using binary bits, now I'm going to show something more specific, like B to B. Just to show that it's using bits to represent those problems. Okay, now I'm going to add an external. I'm going to add in the Boolean table, and I'm going to take it up. It's in I'm going to design this such that if the enable is active, I'm going to go to the next state. If enable is not active, I'm just going to stay in the state I'm in. Okay, so enable is active. So I put this EN here. Now you could put one there if you wanted to. Okay, but I'm EN. So if enable is high, we'll just transition to the next state. But if EN is not high, if it's low, not active, we're going to stay in the same state. So the way I would show that is I would just put an arrow going back to the same state and put a bar over EN. That's the same as putting a 0 there, because EN is 1, not EN is 0. Okay, so I would just do that for each of the states. So you say if enable active, I'm just going to continue in the sequence. If enable not active, I just stay in the same state I'm in. Okay, is that okay? All right, now let's immediately upload. And really help that you can add is put an LED that only lights when the sequence begins and only lights when the sequence ends. For anything else, it's going to be off. Okay, so I'm just going to leave the LED. And you see it starts here, right? 2 goes with A and A at the beginning of our sequence. So to show that the LED will be on at the start of the sequence, I just write LED underneath the external input. And also I would write it over here with the sequence ends. Okay, but everywhere else, I'm going to have that LED off. So, if I just stay state A, I want the LED off. Or LED. But any of these states, if I just stay in the state and turn the LED off. Okay, and also here, when I'm transitioning from like B to C or C to D, D to E, because that's not the start or the end of the sequence, I'm also going to have that. Okay, but this is all just based on how I want to design this. Okay, maybe if you see how a different, a different set of conditions. Okay. Now, also, typically with an FSM, you'll have some sort of reset. And you want to show that input Albert itself. We're going to make it an active low reset. And also I'm going to make it asynchronous. Now, when you take CPE 233, you're going to see that in that processor build, the reset is synchronous. And in fact, I think I can safely say that all, and if it's not all, it's a vast majority of designs have synchronous reset. You typically don't see in practical circuits an asynchronous reset. And that's because, typically your reset goes to all modules in the system you're building, like that microprocessor that you're building 233. And you have a synchronous reset where that reset is happening for each module at the same time as in the clock. Well, that means you're going to be resetting all those modules essentially at the same time. If you have an asynchronous reset, there's more of a chance that you'll get delays between when modules are reset, and that can cause issues. Okay, so the only reason I'm making this reset asynchronous is because I want to show you when I get to the code part, I want to show you how you model an asynchronous reset. I haven't shown you how to, or for that matter, once you know how to do an asynchronous reset, then you could do, any asynchronous thing. So that's the only reason for that. So when you get CP233, don't tell your CP233. So that first says that resets are asynchronous. So they're not saying it's like this is just for an active. All right, so that's our state value. Now, the next thing is to start into the code. Since it's a lot of code that time, and you're going to see basically going to take this thing diagram and translate it into code. Why don't we go ahead and take about a 5-minute break before we do that? Because it's going to take about 20 minutes to finish that. I think it's a good time for a break. Okay, so I'll start up again in like 8 minutes or so. Oh, missing E. Sorry. Good fun. Okay, so let's go ahead and finish up here. So, what we're gonna do next is I'm going to show you the system Verilog, the model this FSM for this counter. Now, the activity today is I'm going to have you go the opposite direction. Here in this example, we're starting with the state diagram, and I'm going to roll the code. The activity for you to do that is to be for you to do today. You're going to be given the code to want you to draw the diagram, but it's going the opposite direction. I'm going to show you. But if you understand the direction, you should be able to go the direction. Now, the first thing we actually need to code here, let's come up with a high level black box diagram. Counter that they sent. Okay, because remember, a high level black box diagram that will give up the main inputs and main outputs. So what inputs do we have here? And what inputs state diagram? What inputs do we have? Yeah, all that block, right? Because FSM has a sequential part to it, right? The state register. So an FSM is all going to have a block. It's a sequential block. But what other inputs do we have? Look at the state diagram. Where are the inputs there? Give me the outputs. Should be able to know what the outputs are also. That's the diagram. Yeah, what's LE? Which one? Output, yeah. Output, just like it has been in number one. Here it's going to tell us whether the sequence is starting or ending. It's like, okay, what else? So again, yeah, that's an output, or excuse me, that's not an output itself. Yeah, that's an input because that's where the really, not really, but the external inputs go. And then this is an output because that's the mealy output. Yeah, so we got enable also as an input. What other input? We got one more input, one more output. And what is this thing output? Why is it called a FSM count? What did someone say? Yeah, the number that counts, right? Here, inside the bubble goes the more output, and the more output, the binary for this count, the number in the sequence. So we have a count. What do I have here? What else do I have? Read that. Right, so those are all outputs. Count, 3 bits, LED, a single bit. There's one more input though. Yeah, Lisa, we will get the asynchronous sequence. Exactly. Okay, so that would be our high-level black box diagram, the FSM. So just like other modules that you designed, right? You write your high-level black box diagram for the FSM, so you know what your main inputs and main outputs are. And that's where you would start, in your system Verilog models, after you name it, I named it FSM counter. Well, just like all the other modules, you would then declare inputs and outputs. Okay, but what's new that you haven't seen before is the next thing. Now, you all have an activity that on your table, there should be updates for each person. And after I'm going to come back to this activity and what one of your activity is different than what I'm writing at the board. So let me write what I want to write here up at the board, and then I'll explain why it's different than what you see. So the next thing to put here is you put a ED definition, type definition, and then you put E and we have that short for new rates. And then you put brace. And now inside braces, I'm going to put the labels that I call the states. Okay, so STK, STC, STC, and so on. You would just put whatever labels you use for however many states. Okay, and then you fold the brace, and then you put the states. And semicolon. Then next line you put states. PL stands for present state. Then you want comma. NS stands for next state. And semi. And you'll see how present state and next state fits into this. Now, if you look at the activity handout. Okay, so if you look at this handout, it's double-sided, by the way. You see right underneath where output or output Z1 and Z2 are declared. It has perimeter, and then it's square brackets 1 to 0. Then it has STA2, tick mark E0, and so on. And then under that, it has logic 1 to 0 NS and logic 1 to 0 PS. And then it always FF starts. But I do this here. It replaces that perimeter line. It also replaces the logic NS and the logic PS. See, on your activity, it's defining each state by groups. Each state has to be associated with a binary number. State A is associated with binary 0, state B with a binary 1, and so on. When you use this notation here, the software will assign binary numbers to these states that you've labeled. And the advantage of doing it this way, as opposed to what's on the activity, is that if you have taken an edit to your state diagram, like say, you have a state diagram, and then later on you find out, oh, this isn't quite working the way it should, and I need to have more states. But if you define your states like this, you're going to have to go in there and change all the binary numbers. And if you go and say 4 states, that this activity is 4 states, Let's say you go from 4 states to 7 states. Well, 4 states, I only need 2 bits. If I have 7 states, how many bits do I need? 3. So you're going to increase the bits, and you know, you get something that's fairly complex. That can be a pain. It can be a really pain, you know, to edit something where you got to worry about, you know, redefining, you know, how these states define. So here, if you add states, the software is going to figure out the new binary numbers, okay, for all your states. So it does it for you, right? So especially if you take CP233, and you're going to see that the FSM in that class is that bad. Um, but anyway, you would want to definitely find mistakes like this and take that class, because you're going to have many more states than what we have here. Okay. All right. So that's that. Now, okay, after this part, which basically defines the states. Now, before I read the next thing, I want to ask you, we model the D flip-flop and also the memory register. What kind of block did you use for the sequential? You know, we have an if statement, that if statement that would give what kind of block was it? Yeah, always at that. Right? You have something sequential, it goes within the always at that, and you use that less than equal type assignment. Okay, how about when we did a combination of like a mux or a decoder? It went within what? And all these right? Same thing for combination, and that's when you use the equal sign for the assignments, right? So look, FSM is made up of sequential and combination. So what you're going to see, and if you just go over the previously, it should make sense. You're going to see that the FSM has an always FF, the sequential part, and it has an always column for the combinational part. Okay, and we always FF first. Okay, so we put always, and before FF, then the at symbol. Okay, then in parentheses. And remember, what we put in parentheses is when we want that always FF to be evaluated. So if we want it to be rising edge, right, we put positive edge. Pause, edge, see okay. Okay, now you haven't seen this before. In previous examples we've done, we've only had a positive edge plot within the parentheses. But I'm going to, in addition, and this is the reason that I'm about to write, is how this reset is asynchronous. Okay? If you have an asynchronous active low reset like we have here, after the positive edge clock, we want to put negative edge. You said, I'll explain why. Okay, but the reason I'm putting this negative edge reset is because that's going to make active reset asynchronous. Okay. All right, but let me finish this and I'll come back and explain in more detail this thing of it. So the next thing is we have the here. And then we're going to use an if statement. So if reset is low. Okay, so I might have mentioned this before, but I think this is the first time I've written it. Within an if statement, if it's active low, if your input is active low, you put an exclamation. You don't put the tilde. The tilde means invert when it's part of a Boolean expression. Okay? But when you want invert in an if statement, it's exclamation. You put it before the input. Okay, so this is if reset is low, we're going to assign present state, state A. And that's because I didn't put it on my, sorry, I forgot this down. Okay, that I resign this FSM counter. If we get an active load reset, we're going to get the state A. So they show that state diagram. Show it like this. Lane reset is low, it's gonna take us to state A. Right? Else, we're just gonna assign present state the next state. We need it. Okay, so if we're not resetting, well then we're gonna determine what the present state is, what the next state, and how the next state is determined is by the combinational circuit. Let's see. Next state inhibitor. What determines the next state? That's combination. Okay, so this part of the FSM, the output, the code part, that's combinational, so it's going to go within the always home. Okay, what's not with the always FF is just the sequential. Yeah, that's right. Well, this is less than symbol, but yet together it makes an arrow. Because remember, and that's important that when you're assigning an output within an always FF, you have to include the less than. If you just put in equal, yeah, you'll run into a problem. If you just put the equal, it's in an always cone. Okay. Yeah, sure. Okay, so now let me explain negative edge reset. See, if this negative edge reset wasn't there, if we just had the parentheses pause edge block, this if statement would be evaluated on the 0 and 1 transition of the clock. So that would make this an active load synchronous reset. Also, including the negative edge reset, this if statement would be evaluated on every clock and also any negative edge reset. Okay, so if reset goes high to low, this will be evaluated, and if it stays low, it's going to reset. And that's what makes it asynchronous. Right? Because this could go low by itself, but this doesn't depend on the clock being on the positive. Okay. So that's a way to make asynchronous type inputs. Is just you add to whatever your riding edge or falling edge clock is, you just add another another variable within the parentheses. Okay, and this is how you're always FF for the majority of FSMs is going to look like. Okay, the only thing you have typically within your always FF for an FSM is you'll have the statement if there's reset. Now, if you don't have a reset, like sometimes you might have an FSM that doesn't need reset. What you're going to have is it doesn't stay assigned to the next state. I mean, that's all you need. Okay, so the always FF part of an FSM is pretty. And even when you take CP233 and you design FSM that's in the microprocessor for the CP233 class, your always FF is going to look like. Where the work comes in is when you do the always these two decoders, like true what your next state is and what your output is. That's what gets linked. Okay, that's where, like in CP233, that's like when you have like 400 lines of code. Or more if you don't look for patterns in the instruction. That's for another day in the future. Okay, but let's continue with this. So this is the always. So the next thing comes to always. The name for this. Okay, what I'm going to do first is I'm going to initialize my outputs. Okay, I'm going to initialize my outputs to 0. So counting the E. So if count be 3, tick mark B, 3 zeros, 3 bits, a semicolon, and LED equal to 0. So this is just initializing the outputs. Okay, and then I'm going to have a case statement. And inside the parentheses for the case statement, you want to put present state. So remember how a case statement works. Whenever whatever's within the parentheses changes, that's when the case gets evaluated. So you see, if we're not resetting, present state is going to be assigned next state. So that means it's going to change, and that's going to activate this case state. Right? That's why we put the present state there, right? Because of this. Okay. All right. Now I'm going to come here. Still in the there it is. All right, now we put the options in the case state. And our options are going to be our state labels. Okay, so I'm going to start with state A. And so state A, and then we'll begin. All right, now I'm looking right at my state diagram. And the first thing you put after the begin, or one of the options in the case state, the option is just going to be one of the states. First thing you put is the more output. And the reason for that is, remember, the more output only depends on the state you're in. So when we're in state A, we know what the more output's going to be. Okay? So I would just go ahead and write, count equal to binary 2. So these 3, tick mark B 0 1 0. Right, so you see, this is a more output. Right, so more outputs go right for the state in the case state. Right after the option for that state. Okay, now it's going to come to the meaning portion. Okay, and remember, meaning outputs not only depend on the state, but also on external inputs or input in this case. See, remember the LED, that's the meaning output. Okay? And as we go from state A to state B, well, if a label is high, we want to put the label is low, well, we don't like the LED, we stay in the same state. Okay, so that's one way, the way to identify when you have a new element. The element is going to be part of this state. So we're going to have an if within a case. Right, so this is like a nested if in a case name. Okay, so we have if enable is high. Okay, we're going to light the LED, and we're going to go to the state. Okay, so if enables high, we're going to make LED 1, and we're going to make next state equal to state. You see how I'm getting it right from the state line? Like enable, it's high, going to state B, going to state B, letting that. Now, if enable is not high, it helps. Well, we're not going to let the LED, and we're going to stay in state A. Okay, so we would just shut off the LED. Shut off the LED, make it 0. And then next state will just be state A. Let's see, we have to end this. That begin needs an end. That begin needs an end. Then we also need an end to this. So this would be another end. Me, that's always the hardest thing to keep track. Is how many ends. If I make a mistake, that's if I admit an end or I have too many ends. Oh, that reminds me actually that there is some software that you can get for free online. It will color code your code. Does anyone know that from like the previous class? When you take CP233, again, because your circuits are much more complicated than your lines of code, it's really useful to have like color coding. You know, like leave things in your hands a certain color, and it just makes it easier to find errors. So most CP professors require that you do some sort of color coding, but it's a good habit to get into in this. So I'm sure if you just Google, you'll find it. All right, so any questions up to this point? The key thing is once you begin your always tone, right? You get to your state test, and you're doing the options, you're just looking at your state diagram. Okay, I'll do one more. If we did state A, let's do state B. And you know, you want me to do more than that, I will. Hopefully, if you see one more, any question you have at this point, it will hopefully answer it. So to do the next state, you just go state B, semicolon, and let's see, state B, the more output is 0. And so count equal to 3, make mark A, 3 to 0. And this is our more output. Okay, then we have if enable high. Okay, so if enable is high, we want the LED to be off, and we want to go to state C. So the LED would be off, the LED 0. The next state would be state C. And for internet. Then we have else. Well, my enable's low, I'm going to have the LED on, and I'm just going to stay in state B. So let's see, LED off, so LED 0. Next state, enable state B. I got a semicolon. Okay, then we would have 2 and yeah, then to this beginning and well. Again, you see just getting them straight from state by. So even the important thing is, yeah. Once you have a state diagram, like when you're designing FSM, usually the tough part is getting the state diagram. Once you have the state diagram, again, it's you go to the system very like code, you need to model it. You know, question which state? Yeah. Yeah, state B. If state B, if the enable is moving, we go to state C and then turn that LED off. Okay, I'm looking here. Yeah, state A, which was the top part, state A, if the enable is 1, right, I'm going to state B and lighting that LED. Okay, that makes sense. For state C, you go to E. All E, that's the state difference all. Yeah, that's a good question, and it should stay off. But I don't know. I would just explicitly shut it off just to make sure. That the thing is, you know, when you're doing this, like what I do, once I have one, like once I have this block, this, I just copy and paste, and then edit. So, yeah, I mean, you could do the same, or like you said, you could, it's already off. You have to turn it hard. Yeah, maybe saving line, but usually when I do this, I use copy and paste anyway, so I don't really worry about it. But yeah, that's a good point. Any other questions? So is everybody confident where they could do state C and state B and state or state C, B, and E because it's the same thing? All right, but then you know, once you're done with state B, state B, the end of state B, what else state B? What do you have to end the case statement? Like, what's the last thing about case statement that if you don't have it, it's going to create a latch? A what? That's for the if statement. Uh, but in case you need something. Default. Right? Don't forget the default. If you bring in a default in a case statement, it generates a latch just like if you leave out an else in an if statement. And here, remember, we're modeling the code, so we don't want to latch. This is combination. Anytime you're within an always column, you don't want to the latch. Okay, so and you can make your default anything. I need it so the next state A. Yeah, the default for everyone. I mean it's state A because that's the beginning of our sequence. And you need it in case. Then let's see, after the end case, you need an end to the always that. That's one I always forget. I do need end case in the case, but then I forget I need an end. It's this begin or wait, no, not that begin, this begin. And actually, did I forget it? I have an end for it, please. Oh, wait, here it is. I'm sorry. Yeah. You need a letter and like here's the end case for this, right? And then we need an end to this begin for the always out of this. That's using this. I missed that. And then we need end one. Okay, so that would be the model this FSM count. Okay, so sure. This is a lot of it will model. All right, so any questions? So you should now be able to do the activity. Again, already on your table, copies for each person. And in the activity, you're given some code. And we want you to go the opposite direction from that code, like the state diagram. And when you look at my solution up here, when you look at it, you're going to see that the solution has dashes. Like for some of the external inputs, we'll have a dash. Do you remember what a dash represents, like in a K-map? Yeah, it doesn't matter. So same thing here. When you see a dash in my solution in the state diagram, use that input to either 0 or 1. It's a map. Okay. All right.